Also, X is said to be homeomorphic to Y. In other words, they're the same as topological spaces. So if you had a homeomorphism between topological spaces, you'd be able to say things that would be kind of like unsurprising. Like if you take the image of a basis, what do you think it is? It's a basis, right? There are more exciting things, like the image of an open set is an open set. The image of a closed set is a closed set. The inverse image of an open set is an open set. The inverse image of a closed set is a closed set. Now those are always true for continuous maps, but that the forward image of an open set is an open set is not always true for just an arbitrary continuous map. If the forward image, if like f of an open set is open, then that's said to be an open map. That's stronger than that's stronger than continuity. There are continuous functions which don't have that open property. All right. Can you give an example of a continuous function which is not an open map? Keep it real. Give me a function from the reals to the reals which is continuous but not open. You're going to give me a bijective continuous map which is not a homeomorphism. What? Whoa. That's a bold claim. Yeah, that sounds like more than the 20 minutes I have left. Yeah.
I search on the stack. I search on the stack exchange and already give the same answer. That it needs to be some kind of non-constructive.
It's a non-construct. It's like one of these axiom of choice kind of constructions.
Yeah,
Axiom of choice, non-constructive construction.
they exactly use that. But they also give some example like the double function, like the one that satisfies the intermediate value theorem, but not continuous everywhere. Like continuous nowhere.
Right. I think we'll eventually get back to some of those kind of things at the very end of this course, but.
But yeah. I mean, what was the exercise? Lee's works on topological manifolds also then find a continuous map which is not open.
Find a continuous map which is not open, but a continuous bijection which is not open. No.
Continuous bijection, but not open.
Continuous bijection where the inverse is not continuous. Okay. I'm looking for something easier still. I just want something that's continuous but not open. I have one. F of x equal to? How about 42? Is this function continuous? It is. Is it open? No. Because if I look at f of AB, what is it equal to? It's equal to the set containing 42. Is this open? No. It's singleton. So the image of an open set is not open. Therefore, this constant map is not an open map. So, yes, I could not construct what you're talking about.
Maybe I was looking for a different kind of function.
Yes, but well, all right. So,
I think the real problem is that find a continuous map, but it is not closed.
continuous map which is not closed. Which doesn't map closed set to closed set? Oh. Oh, this does map closed sets to closed sets. That's true. It is a closed map. Any closed set maps to the closed interval. Well, the closed set of 42. Whether or not this is an interval depends on, your tomato versus your tomato. Interval is oh, yeah. Well, so is an interval a connected subset of real numbers, or is it a connected open subset of real numbers? If it's a connected open subset of real numbers, I agree with your qualification. It's a topological question, whether or not that's an open subset of the reals. It's open in the discrete topology, but it's definitely not open in the metric topology. Is this an open set in the lower limit topology? I don't think so. Yeah. Yeah, if that was open in the lower limit topology, then lower limit topology would just be discrete topology. And that guy whose name I just pronounced wouldn't have had to go through the trouble. Because we've known about the discrete topology for as long as we've been thinking. Okay, so all right, I'm trying to get to something here. So I wanted to look at some more sort of interesting homeomorphisms, all right? So let's start out with the basics, yeah? So, example, you can prove that AB, let's start out with something simpler. 0, 1 is homeomorphic to, say, AB. And here I'm thinking of, okay, so let us just agree that unless we want to be weird, we're going to use metric topology, the subspace topology on open intervals and such, okay? So what's the homeomorphism? You do A plus X times B minus A, I think. I plug in 0, I get A. If I plug in 1, I would get B. Of course, I don't quite get there, but I almost get there, right? So is this function, continuous? Yeah, we've known this since Calculus 1, and that notion of continuity still stands since we're working with metric topology. Is this function invertible? Well, set it equal to y, solve for x. There you go, that's f inverse of y. Is the inverse function continuous? It is, assuming a is not equal to b, of course, right? And definitely 0, 1 would not be homeomorphic to a point, which I don't even know if that would be the empty set, I guess, if a and b were equal, right? It'd be the empty set. So there you go. There's f and f inverse. They're both continuous. We have proved that the open interval 0 to 1 is homeomorphic to any open interval. Another step you might try. Can you guys tell me why would, say, the open interval 0 to 1 be homeomorphic to, say, 0 to infinity? I think you got, there's smoke, there's fire. Let's see here. So inverse tangent looks like this. Oh, you're saying tangent. F of x equals tangent. That maps 0, 1 to, so you do pi x over 2. So pi x over 2. It maps 0 to 0. It maps, plug in 1, you get tangent of pi over 2, which would be infinity. I mean, we don't get to either one of those, but we go in between. So yeah, that's, in fact, yeah, that's going to be a homeomorphism. The inverse, of course, is, you set this equal to y, solve for x. So x is equal to 2 over pi inverse tangent of y, f inverse of y, 2 over pi inverse tangent of y. There you go. That's the inverse, which is also continuous from 0 to infinity, and it has it maps to 0, 1, right? Yeah.
Can you do the map 1 over x minus
1 over x, 1 over x minus 1. Tell me, so what do you want me to do? F of x equals to what? 1 over x minus 1. Let me think about that. So that looks like,
1 over x, and the minus 1 is off to the side.
oh, 1 over x minus 1. And so if I plug in 0, I've got infinity. And then if I get to 1, so it's like that. That makes sense to me. On 0, so yeah, on 0 to 1, 0 not included, that's continuous. And if we set that equal to y, solve for x, so this would say to me f inverse of y is equal to 1 over y plus 1. This is continuous on 0 to infinity, yeah? Sure, that's continuous on 0 to infinity. And it is largest when y approaches 0, and its largest value is 1. And as y goes to infinity, it goes to 0, and you can see that it's surjective onto 0, 1. I mean, anyway. Yeah. Very good. Yeah, well.
I mean, it's like, I use that like all the time.
So,
It's the tangent
yeah, the other example, of course, would be, y is the reals homeomorphic to, 0, 1. So to be lazy, you could just say, well, this is homeomorphic to, say, minus pi over 2 to pi over 2. And then just to get from here to here, use tangent. Because the tangent from minus pi over 2 to pi over 2 takes on all real values, and it's continuous, and then the inverse tangent goes the other way. All right, so what if you, so apparently homeomorphism has nothing to do with boundedness, right? Like, I mean, at least it doesn't have anything to do with like the size of 0, 1 in that strict, like, I mean, 0, 1 is bounded, right? I mean, if I look at 2 points, the usual metric notion, it's at most distance 1 apart, right? The diameter of the set's 1. The diameter of the reals doesn't exist, So sets being homeomorphic doesn't mean boundedness is not something that seems to be preserved by homeomorphisms, right? I think we could say something about preservation of things. I mean, there was, yeah. All right, these examples are fun, but let me give you one that's a little bit more kind of impressive, if I can find it. Ah, come on. I should have stuck a sticky note.
Looks like Shanlin says that discreteness is a property that is.
Discreteness is a property which is maintained under homeomorphism. What would What would discreteness mean?
I don't know. The other one he says is metrizability.
Metrizability is preserved under homeomorphism. Okay. This is so frustrating to me. I found these wonderful, I mean, I've taught out of this book before. I know there's these beautiful formulas in here, and I can't remember for the life of me where they are. Son of a gun. There are other weird topologies we have not talked about yet, like the cofinite topology. And also I mentioned the Zariski topology. Zariski topology is important to algebraic geometry. Maybe we'll talk about that some other day. Oh man, stupid thing. I've got to find this example. It's driving me nuts. Oh, that's right, that's right. All right. How about the open ball in Rn versus all of Rn? I mean, can we prove that, let's center it at 0 for the sake of, sure. So we're looking, here. So I'm looking perhaps for a function. Well, hey, let's look for the function from Rn to the ball. What's another example we can look at? So I don't know if I think about this right away, but here it is. F of x equals to x divided by the square root of 1 plus norm x squared. This has inverse y over the square root of 1 minus norm of y squared. So what we're doing is we're taking the vector, right? I mean, so if you take x out here somewhere, right? And then the length of x is this, this distance, right? So if you square that and add 1, what is that necessarily? I mean, the denominator is what? The magnitude of the denominator is larger than larger than the norm of x, which means that the norm of f of x is what? Smaller than 1, right? Exactly. It's kind of, it's more or less the same idea as the ones we were just doing on the unit interval, just done in sort of the polar sense. You could do something with like an inverse tangent or a tangent appropriately to normalize the magnitude. You know, you could piggyback the examples we've already done. You just have to somehow manipulate the magnitude to shrink it down to the ball. But this is a particularly nice formula. And you know, you might wonder, well, why is that continuous? Well, we proved the norm is continuous. We have, I would assume you could prove the square root function's continuous. And so this is a combination, this formula is built from continuous pieces and is therefore continuous if we actually have built up the requisite theory. Or you could just do a epsilon delta battle with it directly if you really want to. I personally like to use theorems when it comes to these kinds of questions. Another example he's gotten here is the stereographic projection. And so there he looks at the sphere in Rn plus 1. See if I can give you this example here. So he has a Sn x0 dot 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 xn in Rn plus 1 such that the sum of the coordinates is 1. Sum of the coordinates squared is 1, rather. So this is the n sphere. And n, big N, is the north pole, which is the set, which is the point 1, 0, 0. He, and again, this is from, I'm reading from Marco Manetti's rather enjoyable basic topology book that I've used before, but I just want to do something different this time, so I didn't use it again. But anyway, here it is. He defines f from Sn with the north pole removed to Rn. All right, so this function from the north pole, Sn with the north pole removed to Rn, he said it's defined by identifying Rn with the hyperplane. This is hyperplane H, which is a subset of Rn plus 1. This is just like the thing we do in Calculus 3 all the time, saying that the xy plane is R2. Well, that's a hyperplane in R3. I mean, specifically, it's H is equal to the singleton 0 crossed Rn. All right, that's specifically what he means. He's viewing that as Rn there. All right. Anyway, here's the formula. F of x0 xn is equal to 1 over 1 minus x naught, and then x1 through xn. That's the function. And its inverse is a little bit trickier. F inverse of y1 through yn is, the first one is the sum of yi squared minus 1 divided by 1 plus the sum of yi squared. And then it's 2y1 divided by 1 plus the sum of yi squared. And then the same song and dance all the way until you get to 2yn over 1 plus the sum over yi squared. So this shows that the punctured plane, or the punctured end sphere, is homeomorphic to Rn. Or more specifically, the punctured sphere is homeomorphic to the plane. So like this, if you delete the North Pole, that's homeomorphic to the plane. Which is perhaps a little bit surprising, but that one point missing is all the difference. And I mean, so this is, I mean, you can see why is this continuous? It's because x naught's not equal to 1. We've removed the troublemaker. And then these, if you take the square of all these things, all right, they work out to 1, which means that the inverse image is actually on the n-sphere as claimed. And you can prove that it's indeed surjective. It hits every point except for the North Pole. The one place this won't hit is the North Pole, because this can never be 1 with all of these being 0. You see why that can't be 1? Yeah, it's because the numerator is definitely smaller than the denominator, right?
Maybe you square up, you add the sum of the square of them is equal to 1, so because the less than 1.
Right. So that you're missing that North Pole in the inverse image, which is what we want. But on the other hand, there's some other things you can see here, like topologically, the plane is not so different than the sphere. There's just sort of one point removed.
How do you wrap the plane into a sphere?
Right. Uh-oh. Oh no. I have to go. That's it for today.